Hello, my name is Axel Rodriguez. I am a senior production scientist while also a graduate student in the nanomedicine program, soon to be graduated here in this next December. Very briefly, I just want to apologize for not having a webcam for this presentation. I just moved last week, and my secondary PC, my laptop, unfortunately broke along the way, and it was my only form of video broadcasting through a PC. So please let me know if it is necessary to have a webcam, and I'll ensure to have one set up for the next data talk. Thank you. Sorry again. All right, let's dive right into this data talk for Figure 4 and the article by Bugaj and colleagues. The overall goal of the study is to show how changing the kinetics of the RAS-ERK pathway, specifically how extending the decay of the ERK signal leads to an altered transcriptional response and is ultimately affecting how the cells decide to proliferate. Each panel is essentially building a story, so let's first begin with the first panel, Panel A. In Panel A, we see the layout of the experiment where Bugaj and colleagues used optogenetics via OptoSOS to deliver carefully controlled pulses of RAS activation. They varied the on and off time inputs to create different temporal input patterns, and essentially the setup lets then compare what happens when the cell receives a sustained signal versus when they received a pulsed signal. The idea is to see how a change in the signal decay impacts what the cell thinks is happening, and ultimately they're looking for the cell's form of thought process and screening for its reaction. Moving to panel B, the authors measured immediate early gene expression, where here we notice how its CGen and cyclin D1 only spike when the stimulus is continuous in the normal cells. However, when the decay is extended, either through mutation or when it's using a drug that slows down the kinetics, the pulsed inputs start to resemble a sustained signal because the residual ERK activity adds up over time. EGR1 also shows a distinct form of timing where the expression peaks and then drops, which I would assume is a form of adaptation of the cell, which changes when the off kinetics begin to alter. Essentially, the cell's transcriptional machinery is misreading the pulse signal as a longer signal, or it could also be identifying that as a sustained input. Panel C is pretty interesting, where the EDU incorporation is the readout for the cell cycle entry, which is plotted here as a heat map against different pulse durations and intervals. So in the cells with normal and fast decay, a proliferative response only happens when there are long on pulses with short off intervals. But when the kinetics are slowed, uh, the heat map shows that signals that would normally be too slow now drive proliferation. So this extended decay is essentially widening the range of inputs that the cell then, in short, mistakes and interprets that as a proliferative cue. So essentially, it's confusing the cell. Panel D is essentially summing it all up with a schematic model where here we can see it's acting as a form of filter. So imagine an RC circuit that shows the RAS input being processed. So when the filtering is normal, only sustained signal pass through the activation threshold to trigger transcription and proliferation. However, with extended decay kinetics, even rhythmic pulse signals accumulate enough to cross that threshold. So this helps explain why cancer cells with such mutations, or those with certain drugs, I guess, might proliferate in the response to inputs that would normally trigger the cell division. Next, supplementary figure S10 gives us a more of a theoretical foundation where the pathway is modeled as an RC circuit where the time constant t represents how quickly a signal can rise and decay. So by increasing t, you mimic the effect of a slower pathway response. The simulations here show that as t increases, even short repeated pulses start to build up a cumulative signal that surpasses the cell's activation threshold. This directly supports what we see in previous experimental data of figure 4. In supplementary figure S11, the focus is again on the transcription. So the data here is comparing the expression profiles of CGen, EGR1, and cyclin D1 under normal kinetics versus conditions where kinetics are extended through the BRAF inhibitor SB590885. And what stands out is actually the drug, or is with the drug, the dynamic pulse stimulation leads to transcriptional levels that closely match that of a constant sustained signal. So essentially this indicates that the slower decay is effectively misinforming the cell about the strength of the signal. Finally, supplementary figures S12 and S13 go a bit deeper into the proliferation aspect, where in S12 the heat maps reaffirm that with an extended ERK decay, a much broader set of dynamic inputs would drive cell cycle entry. I think that S13 brings up a good question where the effects are the effects just because of the elevated basal signaling, or are they really the result of slower kinetics? Which could be answered by using optogenetics to essentially clamp the basal level without slowing down the off kinetics. The authors then demonstrated that the altered proliferation pattern is primarily due to the extended signal decay and not necessarily because of a higher baseline. So this distinction is pretty important for understanding the mechanism behind the misinterpretation of the dynamic inputs. To form a conclusion, the combined data from the figure 4 and the supporting supplementary figures provide a clear message that slowing down the decay of the ERK signal transforms the way cells interpret dynamic inputs. So what were once non-proliferative pulses become enough to trigger gene expression changes and then push those cells into the cell cycle. This misinterpretation can help explain why aspects of cancer progression could be associated with certain mutations and drug treatments. It can also suggest that restoring normal kinetics might be a viable therapeutic strategy to essentially correct these abnormal cell decisions. Thank you for your time, and I hope you have a good day or rest of your night. Thank you.